Hi guys, in this video I'm going to discuss IR spectroscopy. I'll begin by showing an IR spectrum of acetaminophen. Here's the structure of acetaminophen. It's a compound many of us have taken. It contains a variety of functional groups, or at least two. We have this carboxamide, which consists of the NH group and the carbonyl group, together making up the amide, or carboxamide. We also have this phenol group, which is the OH connected to the aromatic ring. Of course, this is a benzene ring. We also have a sp3 carbon out here with some H's on that carbon. And of course, there's hydrogens on each of the carbons of the benzene ring. Here's an IR spectrum. We first want to orient ourselves to the spectrum. On the x-axis, we have what are called wave numbers. The wave numbers are going to range from about 4,000 to about 500, roughly. What is a wave number? A wave number is essentially wavelength, but it's reciprocal. A wave number is reciprocal centimeters. So it can be written as centimeters to the -1, or we can write this as 1 over centimeters. So it's reciprocal. From centimeters, well, that's a wavelength. And from centimeters, we can convert that number into any other metric unit by doing metric conversions. One thing to keep in mind as we move forward, we'll discuss more and more here. Because of that, 4,000 to say 4 or 500, 4,000 is thus your smaller wavelength because the wavelength is really 1 over 4,000 centimeters, where over here this is 1 over 500 centimeters. So if you do your math, this is actually a larger number in terms of centimeters. So because it's reciprocal, we have that. It's reciprocal mainly to give us whole numbers. Convention was set long ago, well before I was born and my grandfather was born. But the convention is reciprocal, whole numbers. If you do this, you're going to get lots of decimal places. But it's very important. We do need to be able to convert this to microns. To do that, we would first get our centimeter value by just doing this. And then we can get to microns by doing a unit conversion, understanding that a micron is a millionth of a meter compared to a centimeter. Okay, so that's the x-axis. The y-axis here, and you see lots of peaks coming down. Your y-axis is essentially what I call absorbance, where some portion of the molecule is absorbing the IR. Now, it's officially listed as transmittance, because the more you absorb, the less you transmit, and vice versa. But again, for us, this is absorbance. To do an IR, essentially we're scanning the IR range, because in a minute we'll look at the IR range, and the IR range is on the order of about a couple of microns up to 20 microns. Again, you can convert this into microns. What we do is, first we expose our compound to IR. Today that's a very simple technique. We can take a look at instruments at some point. You'll be doing that in lab. It's very simple these days to put your compound on the IR. Once you hit start, from there it's quite simple. The instrument will scan the IR range. As we scan the IR range starting at 400 wave number, we look for absorbance. No absorbance, absorbance. Sharp peak here, which we can identify as about 33 to 3,400 reciprocal centimeters. Broader absorbance here, absorbance here. The absorbance sort of tails off. Then we see down here lots of absorbances. And each peak or band represents some type of absorbance of the IR light. Altogether, we have an IR spectrum. And we will have to figure out and learn what each type of peak means. That can be done by looking at peaks and then deciphering what is the structure. At times we'll also look at structure and say, okay, what type of peaks do we expect here? For example, I'll go ahead and label this IR, just for an introductory practice. We'll learn that an OH group is going to give a peak in about the 3400 region. Also tends to be a little bit broad, and so I'm going to identify this peak right here as coming for the OH group. We also have this NH, very similar position. NHs tend to be a bit sharper. I'm going to assign that as the NH. We also have right here, just below 3000, which is a very prominent region. We have to understand what that's for. This is for your sp3 CHs. And it's pretty good amount of absorbance here. Now again, the only sp3 CHs are right here. But that leads to absorbance here. There's something else we could assign here. I'm not going to do that. I'm going to move over here. At this point I'm going to look at structure. Carbonyl is known to give an absorbance at a very definitive region. Somewhere about here. This is your carbonyl region, roughly 16 to 1800. A little more narrow in there. If this is indeed acetaminophen, which has a carbonyl, that's probably the carbonyl absorbance right there. The exact value of that absorbance is, we can look down here. I typically do give numbers in each of my IRs that I will give to you. We're at about 1660 or so, probably 1666 reciprocal centimeters. This other number is basically the degree of transmittance. That's a low number. Basically, we have high absorbance here. When you have high absorbance, that means you have less transmittance, and this number is actually low. That helps me identify that that's it there. One other thing that we can point out here at the introductory point is roughly about 1500 down. This is called the fingerprint region. You'll have lots of peaks down here. They're not all interpreted. Sometimes we'll look down in that region. But one thing this region is used for is exactly what it says, fingerprint. Acetaminophen will give this type of distribution of peaks. For example, several here, then weaker ones here, and then a couple of strong ones here, a couple of strong ones here, a couple of strong ones here. Acetaminophen will always give that type of band structure. Today, 5,000 years from now. Okay? That becomes essentially like a physical constant. The fingerprint region for a compound in the IR can be used just like a fingerprint for a human being. And if you think about it, the fingerprint is only helpful if you can compare it to something. Just a random fingerprint cannot help you identify a person. Only when you can match that fingerprint to a known standard can you then say, aha, the white powder that I found in the bathroom is indeed cocaine, because the fingerprint of what I found in the bathroom matches exactly the fingerprint IR of known cocaine. Okay, so that's an introductory look at an IR spectrum of acetaminophen. Anything else to say there? I don't think so at this point. Let me erase and let's take a little bit closer look, or more of a overview of the electromagnetic spectrum. Okay guys, here we go. We've seen this in Gen Chem. This is our electromagnetic spectrum, beginning to the far left, as shown here with gamma rays. We need to be aware of energy, frequency, and wavelength. Now if I raise this up, and again these sheets are in your handout packet, we can see down here at the bottom, also listed up there, energy, that's your high energy end. Of course gamma rays, very high energy, X-rays, high energy, ultraviolet. As we move to the right across here, we get to weaker energy light. In terms of frequency, high frequency correlates with high energy, so this is also high frequency end, where your radio waves have low frequency, low energy. In terms of wavelength, high energy end is short wavelength. Your weaker energy electromagnetic waves or spectra have your long wavelengths, long like a football field length. Some of those wavelengths are given with lambda. These down here are meter length. If we focus in on IR, we see that this is like 10 to the negative 6 meters. 10 to the negative 6 would be, guess what, 1 micron. 10 to the negative 4 would be what? 10 to the negative 5 is 10 micron. 10 to the negative 4 would be 100 micron. Or micrometers, micrometers. Okay? So indeed, the IR, if you convert your wave number to microns, you'll see it's a couple of microns, typically here, 2, 5, 20 microns in terms of wavelength. However, usually we will discuss actually frequency more often than wavelength when we talk about IR. Let's touch briefly on what each type of electromagnetic radiation can be used for in organic chemistry, or any chemistry for that matter. Gamma rays not used much at all for organic chemistry, very high energy, very damaging, unsafe. We of course see gamma rays in our radioactive elements that can emit gamma rays. There is such thing as gamma ray spectroscopy of plotting the absorbance or the types of radiation that is given off from radioactive elements. But at the introductory organic level, you're not going to see anything with gamma rays. X-rays, of course, we use those for medical purposes. X-rays in organic chemistry are used for X-ray crystallography. This is about the closest way we can come to seeing a compound. If we shine X-rays on a crystal, that crystal will diffract. Well, the X-rays will cause electrons to be emitted from the molecule. Ionizing, X-rays are ionizing. They cause electrons to be lost, forming ions. But the electrons, the diffraction of the electrons can give an image, and that image can be interpreted into a structure. Very powerful and amazing stuff of how we can get structures of compounds from X-ray diffraction. Next, ultraviolet. A little bit less in energy than X-ray. Still fairly high in energy. It's the UV light from the sun that can be most damaging. UV is usually coupled with visible, and we have a type of spectroscopy called UV-vis, because after ultraviolet is visible. UV-vis is also known as electronic spectra. This type of light does not cause electrons to be ejected. It's not ionizing radiation, but the electrons are excited to higher energy levels, and that's the process in which we have absorbance. This process is important when we consider why things exhibit color. For example, why is an orange or a carrot orange? It has to do with absorbing visible light by excitation of electrons. But the electrons still remain part of the molecule. The energy is not as strong as X-rays. Okay, by the way, your visible, this is black and white. Your blue is your higher energy visible. Okay, now we can start seeing colors. You may remember the mnemonic from Gen Chem, Roy G. Biv. That's actually backwards. Red is red, orange, yellow, green, blue, indigo, violet. I'm not showing indigo violet. Violet is your color here. After violet, moving to the left would be ultraviolet, even higher energy. After red, going to the weaker end would be infrared. And infrared is used to do IR spectroscopy, which we're talking about today. Infrared does not deal with the electrons, really. It deals more with the bonds. Of course, bonds contain electrons, involve electrons. But infrared deals more with vibrations of bonds, vibrations of molecules. We'll talk more about this after I finish going over this chart here. But essentially, all molecules have different types of vibrations. We can have a, consider just a bond vibration, two atoms here, just stretching. Okay? The bond length may be like this, but any bond length that's quoted in a table is just a static number. That bond is really stretching, which is a general type of vibration. But that stretch occurs at a certain frequency. It can stretch slowly, maybe, or the stretch can be faster. Okay? That's two different frequencies. Now, a molecule can have one bond that's just sitting here stretching slowly, and it can have another bond that's sitting here that's stretching faster. That's two different frequencies. It turns out that that frequency correlates with IR frequency. It also turns out that if you shine IR onto a compound that's sitting here doing this, that the bond, part of the molecule, will absorb the IR light. And that's what we're plotting, absorbances in the IR. Now, why do we get so many peaks in the IR? Because there's so many types of frequencies that a molecule can have. If you have 10 bonds, every bond can be vibrating or stretching at a different frequency. Some fast, some slower. And so this one absorbs a faster or higher frequency light. This one absorbs a lower frequency light. And every absorbance gives you a peak in the IR. We'll come back and talk a little bit more about that. Let me finish this up and then we'll move into more of the frequencies. After infrared, we get to the weaker microwaves. We can use microwaves to pop our popcorn, etc. Microwaves are used to study sort of rotation and tumbling of molecules. Not that common at the introduction organic level. I don't have any experience with microwave other than the one in my kitchen. Next is radio waves. We can listen to our favorite radio station, or in terms of chemistry, we can do NMR. NMR is perhaps the most important of the organic analytical techniques or spectroscopy. We use radio frequency when we do NMR. And NMR is essentially what they are doing when we perform MRI in a hospital setting. With the M standing for magnetic. You have to have, the compound has to be in a magnetic field for the absorption to take place here. Either the compound or the human body needs to be in a magnetic field. Okay. What else can we do here? Let me go back to more types of vibrations. Okay, IR deals with vibrations of bonds. A lot of students think we're dealing with atoms, and we'll state, well, the bromine gave this in the IR. The bromine atom doesn't do anything. It's the bond. So the bromine bonded to, per se, a carbon. That bond has a stretching frequency. There's other types of frequencies that a compound can have. I'll illustrate it sort of with my hands here as I do, but I'll also show something on the web that shows some prettier pictures with some actual vibrations going on. Okay, the most common is your stretch. We'll refer to those. The peaks that we assign usually come from bond stretches. Okay? Other peaks, particularly peaks in the fingerprint, which we're not going to interpret that many of those come from other vibrations. We can have vibrations where maybe the molecule as a whole starts vibrating. We have maybe multiple atoms. And instead of, well, let's look at this. We could have 2 atoms, 1, 2, 3. That's 3 atoms. We could have 3 atoms. We can do an individual stretch at a certain frequency. But we can also maybe do something where both bonds are stretching. And maybe that's at a different frequency. And some molecules, the absorbance can occur when it matches this frequency, or the absorbance can occur when it just matches that frequency. Or in terms of this frequency, that's called a symmetric stretch, symmetric 2-bond stretch. The alternative to that is an asymmetric 2-bond stretch. And so when you have a compound such as water, I mean, if we just draw water, oxygen HH, the 2 H's could be stretching like this in some of the molecules. In other molecules, or back and forth, each molecule likely does all of these. We could have another molecule doing like this, but that maybe is slower, or maybe it's faster. But that's right there is 2 different frequencies. What else can we have for something like this? If we stick with HOH, maybe instead of the bonds stretching, maybe we have something like this. I mean, the bond is not stretching. That's called maybe a wag or a bend. But it could do this slowly, or maybe it's doing it fast. And you just have to remember, every frequency that the compound is exhibiting from the vibrations, the IR light can match that, and an absorbance will take place. Now, let me show these from a great resource that I love, and that's called the Wiki. Wiki being short for Wikipedia. Okay? Look at these. If you look up IR spectroscopy on Wikipedia, you can get to this page, and this shows some examples of stretching. This is a 2-bond stretching, symmetrical, anti-symmetrical, or asymmetrical, scissoring, twisting, wagging, rocking. Okay? Most of these frequencies, it looks like in this page here, all the frequencies are pretty similar. But that's not actually correct. This one may be very fast, this one may be very slow. Lots of frequencies leading to lots of absorptions. Most of these are all in the fingerprint region. Again, most of the peaks that we will decipher and assign are going to be usually 2-atom bond stretching. Okay. Now at this point, let's talk more about how does the absorbance take place. We've said that whenever the incident IR light, that is the light that we're shining on the molecule, whenever that frequency matches a vibrational frequency, you'll get an So let's consider we got a bond stretching, minding its own business. We shine some IR light on the bond. What happens? The bond goes from this sort of standard stretching frequency. The light comes in and absorbance takes place. That's a very physical phenomenon which we may or may not get into in fine detail. The absorbance takes place. What happens? That's energy that was absorbed. What's the manifestation of that energy? The bond goes from here to a higher energy vibrational level. Now the bond is stretching with higher energy at a higher frequency. We say it's absorbed the energy. Okay? How does it absorb the energy? At this point, we're really getting into physics. It has to do with the electrical nature of light and also the electrical nature of a bond. The dipole of the bond is important. It turns out that a bond that is, or a stretch that has no change in dipole will not absorb IR. In a nutshell, the more polar the bond, the more prone it is to absorbing the IR. At this point, I ask you to refer more to your physics coursework and ask questions about the fundamental of how and why the bond absorbs the IR. But it takes it to a higher vibrational level. For us, it's important to understand that there are two things that affect how a bond vibrates. Why does this bond vibrate slow, but this bond vibrates faster? Two things. The answer to these can come from Hooke's law. Now, Hooke's law is taught in physics when you talk about springs. Just a standard spring stretching. Okay? Turns out that you can treat a bond just like a spring in terms of understanding these types of things with the frequency. Hooke's law is here. Basically, this F is a force constant. That refers to maybe a stronger spring. A stronger spring equates with a stronger bond. And the stronger spring or stronger bond that you have is going to vibrate at a higher frequency. That sort of just makes sense. If I have a strong spring and I sort of tap it, that spring may go because it has strength to it. If I have a weak spring, it's real limp, and I kind of tap it, it may not even vibrate hardly at all. That's known as the force constant, equivalent to strength of the bond. The other key thing to consider here is this M value. Small the mass, because it's in denominator, also leads to higher frequency. Smaller mass in terms of, well, in physics you'll put different types of weights on the end of your springs. In chemistry you'll have different sized atoms on the end of your bonds. Okay? Now let's think about it. What if you put two huge atoms on the end of your bond? Two huge high molecular weight atoms. Is that going to slow the stretch down or speed it up? Well, it actually slows it down, like having two bowling balls. If you got two bowling balls, that spring is not going to be able to do like this. The bowling balls slows down the vibration. On the other hand, if you put two marbles on the end of your spring, that's not going to have much effect on the inherent vibration of the bond. Smaller mass, higher frequency. This is going to be very important when we talk about hydrogens. Hydrogen is your smallest atom. Most all others are like 12 to 15 times higher molecular weight. If you have a hydrogen involved, very small mass, you're going to have higher vibrational frequency. Now, when we get to IR, I should have said it back on the other page. When we look at an IR, these trends are the exact same on your standard IR. That is, this is the high energy end of an IR, this is the high frequency end of an IR, and typically we will talk frequency, although wavelength, reciprocal wavelength is actually applied. So, High frequency in to the left. If you have a hydrogen that's real light, and so the bond is going to vibrate faster than if you had a heavier atom. That's why when we look back at the original IR, each one of these bonds that I assigned had a hydrogen in the bond. And that's what we'll see when we get to tables. If it contains a hydrogen, it's typically going to be in this region, the higher frequency end. On the other hand, if we can have something like maybe a huge iodine atom, like maybe a carbon iodine, that's actually going to be way to the right. Okay? We can even do some examples here. If I show you maybe a CBr bond versus a C iodine, and ask which will have the highest wave number in IR, highest wave number absorbance, that would be the CBr. It's going to vibrate faster because why? Iodine is a heavier atom. Carbons are constant. This slows this vibration down, slows the frequency down, and so it absorbs lower frequency light. And so that peak is going to be more to the right. That'll have the higher wave number. We can also, well, at this point, let's move to our first table of where particular bonds absorb. That's one of the next, I believe it's at the bottom of the page with Hooke's law. So this is an introductory table. The next table we'll look at will have many more numbers. This is the first look. Okay, single bonds, double bonds, triple bonds, bonds to hydrogen. Already mentioned that. Look here. Single bonds are typically, okay, this is going to be, what is this, about 1500 to the right? Fingerprint region. Take home. All bonds that are single bonds, again, everything here refers to stretch, okay? These are all stretches that we're referring to. All single bond stretches absorb in the fingerprint region unless there's a hydrogen involved. Because the low molecular weight of hydrogen, those actually absorb at the very other end, the higher frequency end, CH, OH, NH. Now, of course, if you had two H's involved, that would just be hydrogen, and typically that's just a single molecule, and we don't discuss that much. Okay, so really, we're only dealing with one hydrogen. So hopefully that makes sense in terms of mass of the atom. Okay, down in the fingerprint, these would be fingerprints. Single bond with no H, fingerprint. Which would have the higher wave number? We've already answered that. CBr, because the Br is lighter than the iodine. Okay, if you move to double bonds, we start moving to the higher frequency range. We're in here about 1500 to about 1800. Okay, does that make sense? Look at C single bond versus C double bond. Is there any change in mass of the atom? No. What is the difference? Double bond is stronger than single bond. Stronger bond is going to vibrate at a higher frequency. That's what we stated when we were looking at Hooke's law. You also have C double bond O, that's your carbonyl groups, variety of functional groups. C double bond N, okay, that region. What about triple bond? C triple bond C, common, C triple bond N. It's very rare to have C triple bond O other than carbon monoxide. Triple bond being stronger than double, even more to the higher frequency N, higher wave number N. This would be typically, these are roughly at about 2200. Okay, it says up to 2500. Could be as low as 2100, but basically right around this region. Once we get to the next table, we'll see some more specific and pinpoint these numbers a little bit better. But that's your triple bond region. Then here, this is again your CH, OH, NH. There is a variety of these types that we need to discuss. Okay? So this is sort of your starting point of learning where your different bonds or functional groups give absorbances in the IR. We might real quickly look back at acetaminophen. If you remember, it had OH, NH. It's been erased, but do you remember the NH, OH, CH? We will have to clarify what is the hybridization of the carbon we're talking about. We'll see that on the next table. Then you remember your double bond region, and this ended up being the CO. Okay? So you need to start looking at IR versus tables and seeing that indeed peaks do fall in the appropriate regions, and we can assign these peaks. Okay, the next table in the packet is a little bit more comprehensive, clearly more comprehensive. Pretty much this is the level that we do need to know our IR peaks. Although there is probably these comments, some of them are more important than the others. It may look a bit daunting at this point, but that's probably only because this is the first time you've looked at it. Once we start working with this, this will quickly become less daunting and look more like the table that we looked at a few minutes ago. Okay, let's start by making some comments about our bonds that contain a hydrogen. First off, you do need to know your functional groups. The reason we teach IR at the beginning of organic chemistry here at GRU is because it goes hand in hand with learning your functional groups. Your alcohols and carboxylic acids, they both contain an OH group. Okay? OHs tend to be pretty broad and strong. We saw one of these in acetaminophen. Here's the range. Also, let me point this out. I will spend some time going over this table, but what I will also do is we will look at each type of functional group and we will look at the particular absorbances for that functional group. Okay? Eventually we will look at amides, we will look at sp2 hydrogens. Okay? This is just sort of in table format here. I just want to orient you to the table. NHs, there's lots of NHs. You can have amines, they can be primary, secondary. Of course, a tertiary amine does not have an NH. You can have your carboxamides, aka amides. These are all roughly, I say, in the 32 to 3400 range. We'll make comments later there. This is important, your CHs. As I mentioned, it varies depending on the hybridization of the carbon. We've already mentioned your sp3CH just below 3000. There's a magical line here. This line is at 3000. Just below 3000 is your sp3CH. Just above 3000 is your sp2CH absorbances. This pretty much doesn't mean much to me. Your SPCH, which is going to be like in an alkyne, about 3300. Now it is pretty sharp often. One exception to these three. The hydrogen of an aldehyde, and that's aldehyde here, your CHO, that's an aldehyde, sort of a condensed version of an aldehyde functional group. The H is on an sp2 carbon, but it's not just above 3000 like all of your other sp2Hs. It's actually a little bit less than this range, 2700, 2800 range, and we will see a peak, an example of that when we start looking at individual spectra. Word of caution, students often forget this absorbance for the aldehyde. It says 1 or 2 peaks. Very often it's 2 peaks. There, we'll see an example. Okay, let's move more to the right. Triple bond region. Your CC triple bond, it says 2250 in this table. I've never seen a CC triple bond that high. That it may even be a typo. It may have should said 2150. Usually your alkyne carbon-carbon triple bonds are below 2200, where your C triple bond N is actually usually above 2200. It can also be below, very often lower there. From there we can move down to the double bond region, and the most important of your double bond bonding arrangements in this region is carbonyl. Very important because it tends to be a strong peak whenever it's present. And also when a carbonyl is present, that just tends to be a major structural component of your compound. You have different types of functional groups that contain a carbonyl. A carbonyl is not a functional group in itself. Okay? It's only a component of those. I may or may not spend much time here. Your acid chlorides tend to be high carbonyls at about 1800. A number of these different carbonyls I cover in Organic 2, and we look at them in more detail, their exact positioning. We have some that are high. These are kind of high carbonyls. Your ester, that is an ester. Okay, you got to get used to looking at your condensed. This is not strict formula, but it's rather kind of a condensed structural formula. We're not showing bonds, but we are seeing some structural information in the way it's listed. This is your aldehyde. This is a ketone. You need to be working on these elsewhere. That's an anhydride. That will be seen in Organic 2. Esters tend to be a little bit high. Your aldehydes and ketones sort of standard. You know, right around 1700, very standard. Can be a little bit below if it's conjugated. We'll at some point explain what conjugated means and why conjugation always typically lowers the value. Carboxylic acid, that's again standard. These are all pretty standard here. Then we get to the amides. Some people say amides. I typically say amides. The long term being carboxamides or carboxamide. These typically have low carbonyl. Okay? Down in the mid 1600s, I've seen amides as low as 1625. It's pretty low for an amide. If your carbonyl is at 1625, and there's only one carbonyl in your compound, it is clearly not an acid chloride. Okay? Clearly not an ester unless it's super conjugated and something is making it go down that low. Okay? Also in the double bond region, you have our C double bond C. These can be in alkenes or also arenes. Abbreviation for that. Typically AR, a more term that I use more often would be aromatic or aryl. These authors chose to go with arene, probably to make it similar to alkene here. Similar range, typically lower than carbonyl. Okay. Usually not quite as intense as carbonyl. I mentioned this earlier, or alluded to it. let's mention it more specifically. We haven't talked about why one peak may be very intense, but another peak may be, not as intense. We talked about positioning, mass of the atom, strength of the bond. What makes this so intense at absorbance? That has to do with polarity. The more polar the bond, the more prone it is to absorb the light and give you a stronger absorbance. Your carbonyl CO has more of a dipole, of course, than the CC. And so your carbonyl typically is a stronger absorbance. Okay? Probably best to see these when we do precise examples. Nothing much else to say here. Your CN is not that common. It's sort of commonly seen in lots of molecules, but we don't look for it quite as often in the IR as we do certainly the carbonyl or the CC. Now at this point I'm going to go back to the first page of the handout packet, which has peaks identified for you. We will, in the remainder of the packet, there are a number of IRs, and I will go through them and I will assign peaks on this video as part 2 of this segment or IR lecture. But here let's do it, sort of just get you oriented. Okay. One thing I want to do is draw me a line at 3,000. There's a magical line there. Remember, peaks just below 3,000, sp3ch. This is what this typically means. Do we have that in the compound? Yes. sp3ch. Here, and here, and here. Okay? There is 9 CH bonds there. Every one of those bonds is vibrating at some frequency. Some may be identical frequencies, some may be different because of different structural location within the molecule. But all of that is vibrating in this particular region of the IR. And so when we scan the region, we get absorbance right there due to these methyl groups. Okay? We also have this peak over here just above 3,000. Just above 3,000 is your sp2ch. Now we also have the structure here of caffeine. Okay? There's obviously no OH or NH in the structure. What do we have here? There's one H right here that is sp2ch, and that is that peak right there. It's coming from that bond, doing some stretching, and then absorbing the IR, going to a higher vibrational level, and absorbing the light, and we can plot that absorbance. Okay, not much other absorbance. There's no absorbance in the triple bond region because there's no triple bonds here. Down here, there's 2 strong absorbances at about 16 to 1700. What region is that? Well, strong peaks there, typically carbonyls. Okay, we indeed have 2 carbonyls. Okay, one of them is between 2 nitrogens, a urea. The other one is next to just 1 nitrogen, an amide. Okay, but 2 carbonyls, that's them right there. If you want the precise values, you can look over here. It looks like 1699 and 1649. Both carbonyls are conjugated with nitrogen, so they're sort of amide-like. And so they're more in the 1600 range. Fingerprint region, okay, anytime you run caffeine, it should look like this. That is with a kind of a broadish peak here, whatnot, to here, strong peak here. What else do we have in the compound that we have not identified? What about an N-carbon single bond? Well, what do we know about single bonds? Single bonds always fingerprint unless it contains a hydrogen. No hydrogen, fingerprint. Something down there is because of that bond there, etc. but we typically don't assign those. What else do we have? I do see a C-C double bond. Okay, right here. There may be others. Where is this? It's about 1650, okay? Even lower, if you look at aromatics, okay? Something may be in here. If you look back at the table, okay? You notice on the handout, I really didn't struggle to identify it. One thing we do need to learn is when do you need to worry about identifying every single peak and when do you not need to worry so much. Ultimately, it comes down to what's your goal. Okay? So as we end here on this first video, let me talk about the goal. I'll erase here. This video may run out of memory or battery power. If it ends, that's okay. We'll pick up on the next video. In the workbook, you can find some IR problems. These are example problems. What we have here, and what I'm going to ask you to do is assign one of the compounds at the top to an IR spectrum. Okay? This will involve you, I would recommend first interpreting peaks. For example, I see a pretty intense peak here at about 17